So we will start our discussion on variation of parameters. Before we discuss go into the details, before we go into the details, let us recall. Let us recall that complete solution or general solution is actually CF plus EI. Sometimes they are actually called general solution or complete solution. Yeah. This is complementary function. This one is particular integral. Okay. We have seen that for complementary function, we'll use d operator, and in place of d, we'll put m. Then find the values of m1, m2, and n. Suppose it is n order differential equation. Then the complementary function was given c1 e to the power m1x plus if d is ddx plus c2 e to the power m2x plus and so on, depending on the whether they are similar or they are repeated root or different root is e to the power mn x. Okay, and we have seen there are type of rule 1, 2, 3, 4, 5, and finally we have seen the general form, which generalized rule for finding particular integral. Okay. Now today we will learn another new method to find out the general solution, and this is actually for especially to find out the particular integral, which is known as method of variation of parameters. Variation of parameters. Okay. So for this method, we need to write the given equation, whatever may be the given equation, whether it is a d y dxn as a 2 dn minus 1 dx minus 1 plus n y equals to, and the right hand side is function of x. This is, let us call it x and function of x. Our task is to make it this highest order derivative. We need to free it. Okay, this term we have to divide. So this should be the coefficient of this term, highest degree term, highest order derivative should be 1. Okay, and rewrite, that is, we need to rewrite the equation. So a2 by a1 t power n minus 1 dxn plus an by a1 equals to 1 by a1 into x. So we have to do this, whatever. So again, this is, it remains the function of x since a1 is constant here. Okay. Now our task is to, let us consider the simple Yes. Suppose d2y dx2 plus b into dy dx plus c into y equals to x. Where we are, here a equals to 1, so we are not writing a. So that is why we are taking only b and c. Okay. So our task is to find out. Okay. Okay, the formula method working rule. If this is the given, after rewriting the equation, it is this is a standard for method of variation. Method of variation of parameters. Okay, variation of parameters. Now, the working rule is first one, find complementary function. As since this is a second order, so there would be CF would be C1 into Y1 of X plus C2 into Y2 of X, some functions of X, Y1 and Y2. Next, we have to find particular integral as Pi equals to U into Y1 plus V into Y2. Note that these are actually taken from here. This Y1 and Y2 are taken from here. So let us not write X. When the context is clear, we know that this is a Y1 and Y2 are functions of X. Okay. Then we define third thing. This is actually defined. Find Wronskian. There is a new term we are introducing, that is Wronskian, which is defined by Wronskian of two functions y1 and y2 is actually given by the determinant of this y1 and y2, then y1 dashed and y2 dashed. If it is non-zero, then we say that y1 and y2 are linearly independent, or not linearly, just independent functions. Independent. For vector, we have used linear dependence independence, but here we will say just independent solutions. Y1 and Y2 are independent solutions. Now, what we do? The fourth step that we are going to do is, remember in the second step, we are defining U and V. U and V are unknowns, unknown parameters. Okay, unknown parameters. These are unknown parameters. So how to get these unknown parameters? That is in the fourth step. Okay, u will be defined as negative y2 into x divided by run square of y1 and y2 into dx, and v would be defined by y1 into x is the right hand side function, divided by y1 and y2 into dx. So once we find them, we'll substitute these values. Okay, find u1 and v2, then write the general solution as y equals to c1 cf plus pi. Okay, so cf was c1 into y1 plus c2 into y2 plus u is this one, u into y1 plus v into y2. Note that we'll get this u from here and v from this integrations. So this will be our final answer. Okay. So how this u and v are coming to the picture, that we'll discuss sometime later. But before that, okay, let us first discuss that how these are actually calculated. Then we'll go for practical, application with examples. So here the method is actually written. So you can just think of this. Okay, just let me write it down one by one. So the given equation is d2y dx2 plus b into dy dx plus c into y equals to x. Okay, now we can write it y double dash plus b into y dash plus c into y equals to x. Rewrite. Okay, so let us rewrite. So this is equation 1. Then for CF, we will take y double dash plus b into y dash plus cy equals to 0. Call it 2. So if we solve it, then the CF will be, let us call the general solution of this equation. Note that general solution of equation 2 is actually, so general solution equals to CF plus pi, but the right hand side is 0, so pi will be 0 here. So for this equation 2, general solution is the complementary function, and we know that general solution can be written as y equals to c1 into y1x plus c2 into y2x. So let us call it 3. Note that this is the CF. So this is a general solution of equation 2 where c1 and c2 are arbitrary constants. Okay. C1 and C2 are arbitrary constants. But this is not a solution of this equation of equation 1 because the right hand side is, so we have to do some changes. So what we do here is, let us take equation 3 was there. So what we do here now is y equal to u plus, sorry, u y1, let the pi actually uh, plus v into y2 be the particular solution. This u and v are functions of x. Okay. Then what will happen if you differentiate? Let us call it equation number 4. Let us not differentiate with respect to x. Then we will get y dash u into y1 dash plus v into y2 dash. And since they are also functions of x, then we will have u dash y1 plus v dash y2. Our aim is to, we need to select sorry, we do not select this one. We need u1, u and v satisfying this equation, u dash y1 plus v dash y2 equals to 0. See, if this part is 0, so let us call it equation 4. Then from here we will get y dash equals to u into y. Since these are unknown parameters, we need to calculate them. So we need some two unknown parameters. So we need two equations and two at least two variable and two equation system. So this would be one equation. The another equation, let us see how to get the another equation. So this becomes v into y2 dash. Again, if you differentiate with respect to x again, then we get y double dash equals to u dash y1 dash plus u into y1 double dash plus v dash y2 dash plus v into y2 double dash. So we have these values y2 double dash, y double dash, y dash, and y. So these values substitute the values of y, y dash, and y double dash in equation 1. So what is our equation 1? This one. So now what we'll have, we will get, so that was equation 1 was y double dash plus b into y dash plus c into y equals to x. So for this one, we'll have u dash y1 dash plus u into y double dash y1 double dash plus v dash y1 y2 dash plus v into y2 double dash. Okay, this one we have found for this one for y2 double dash plus v into y1 dash. For y1 dash we have u into y1 dash, sorry, y dash. For this one we will have into y2 dash, and for this one c into u y1 plus v y2. The right hand side is x, is a function of x. So let us take u outside. Then here it is y1 double dash plus b into y1 dash here plus c into y1 plus b into y1 double dash plus b into y1 dash plus c into y2. No, sorry, this is y2 dash. This is for v, it is y2, and this is y2 plus this one. We will have, okay, these terms are remaining. U dash y1 dash plus v dash y2 dash. This is equals to right hand side x. Now since y1 and y2 are solutions of equation 1, they will satisfy this equation. So from here we will get solutions of equation 2 actually, because y1 and y2 are complementary functions. They actually constitute the complementary functions. Equation 2. So they will satisfy. So they will. So we'll have y1 double dash plus b into y1 dash plus c into y equals to 0, and y2 double dash plus b into y2 dash plus c into y2 equals to 0. So what will happen? This becomes 0. So this is also becoming 0. So finally we'll have this one, u dashed y1 dashed plus v dashed y2 dashed equals to x. So let us call it equation number 5. So 4 and 5. So equation number 4. Take equation number 4 and 5. This one. So we'll have a system of linear equations where two variables are there and two equations. So u into y1 plus, sorry, u dashed into y1 and v dashed into y2. This is equation 4. And here we are getting u dashed y1 dashed plus v dashed y2 dashed equals to x. This is 5. So from here, if we use Cramer's rule, then u dashed will be determinant of 0x y2 dashed divided by the determinant of y1 y2, and this one is y1 dashed y2 dashed. So what we are getting actually here, so if you expand this determinant, we'll get 0 minus y2x minus, this is nothing but the Wronskian. We can call it W1, W2, W1 of y1, sorry, W of y1 and y2. So we'll write it y2x by W of y1 and y2, Wronskian. So since this is the U test, so this actually written by the U dx equals to this one. So from here, we'll write U is integration y2x dx by W of y1 and y2. Similarly, we will get V equals to integration y1x by Wronskian of y1 and y2 into dx. So once we find this u and v, then the particular integral will be u into y1 plus v into y2. Okay. So all these are actually giving the working steps. So complete solution will be CF plus PI. Okay. Once PI is computed, then we will calculate. Okay. So now we will see some examples using how to solve how to find particular integrals using method of variation of parameters. Okay, so there is another important theorem related to Wronskian of two functions. Okay. So this says if two functions are there, y1 and y2, then they are said to be linearly independent. Anyway, earlier I mentioned that only independent, but for functions also we can use linearly independent. Like we have used C1 P1, C2 P2 plus Cn Pn in the linear algebra. If we find C1, C2, if this equation is actually giving you C1, C2, Cn equals to 0, then we say that these vectors are linearly independent. So same idea is actually used here. How to call it, whether the two functions are linearly independent or not. So for this, we need to check the Wronskian. Wronskian of two functions If they are non-zero, then we call it a linearly independent. This Wronskian concept will be useful for variation of parameters. For if suppose we have third order derivative, third order differential equation. So for example, a into d2y dx2 plus d3 c into b into d2y. Okay. Here do dy dx plus then c y equals to the right hand side. Here actually the complementary function will be c1 y1 third c2 y2 plus c3 y3. So y1 y2 and y3 here. In that case, we will define the Wronskian as this way: y1 y2 and y3. So this will be y1 y2 y3 y1 dash y2 dash and y3 dash and y1 double dash. So it would be 3 by 3 determinant, 3 by 3 y3 double dash. In that case, Wronskian will be this one. So for this type of difficult problems, higher order ordinary differential equations, the Wronskian concept is very, very useful. Okay. Now we see one example. Solve this by method of variation of parameters. So we are going to solve it by method of variation of parameters. So let us use the d notation, d square plus 1 into y into cosec x. So the auxiliary equation will be m square plus 1 equals to 0. So a means plus minus I. Hence the complementary function is c1. So let us call it a cos x plus b sin x. Here this is y1 and this one is, call it y2. So let y1 is cos x and y2 is sin x. So in the next step, what we do, we define pi particular integral u into y1 plus b into y2. Okay. So where u is calculated by, okay, so another term we have to calculate w1, w of y1 and y2. So here it is y1, y2, y1 prime, y2 prime. y1 is our cos x, y2 is our sin x. So cos x its derivative minus sin x. Sin x is derivative cos x. So this, if you expand this the determinant, then we will get. So this is becoming 1. Okay. So u is defined by minus y2 into the right hand side x divided by Wronskian of y1 and y2 into dx. So we now calculate u equals to minus y2, that means sin x, y2 is sin x, the right hand side is cosec x into dx. and the run scan is 1. So sin x and cosec x, it will give you 1 plus 1 into dx. So this is nothing but minus x. Similarly, v is defined by y1 cos y1 into x by w of y1, the run scan of y1 and y2 into dx. So here what we get, this is cos x, y1 is cos x, y2 is cosec x, this one is 1, the denominator is 1. So here it is cos by sine, so 1 by cos equals to, this would be 1 by sin x. So this is cot x into dx. So this is nothing but, what is it? Log of sin x. Okay. So we can write the solution now. So the particular integral will be u times y1 plus v times y2. This is nothing but u is minus x, y1 is cos x, plus v is log of sin x, and y2 is sin x. So this one, x cos x minus x cos x plus sin x log sin x. Hence the general solution, y equals to cf plus pi, which is nothing but a cos x plus b sin x plus this one, it is minus x cos x plus sin x into log of sin x. So this would be our final answer. Now let us see one more example. So if we have the tan x, the right hand side, then we will have the complementary function as same. Okay. So if we have this tan x, then what will happen? The run scan is again 1. Okay. Then u can be calculated as this way. So sin x into tan x divided by 1. So this is nothing but sin x by cos x, and sin square x by a. In place of sin square, we can write it 1 by cos x, cos square x. So 1 by cos into 1 by cos. So let us separate them. Then we will get this equation. So finally, u is calculated this way, and v is actually y1 into tan x. Y1 is cos x. For tan, we will substitute sin by cos. Then we will get sin x dx. So this is minus x. So this particular integral is actually u into y1 plus v into y2. And the general solution cf plus pi. So this would be our final answer. Okay. So here is another example. If we have this equation is given, the ordinary differential equation is given as this way. So note that here the coefficient is 1. If it is not 1, then we have to divide it and do the manipulation. Okay. So here the complementary function is this one. So from here we will get y1 equals to this one, y2 equals to this one. And take the Wronskian -2, so non-negative, non-zero, so they are linearly independent. And the particular integral will be defined by this way, where we need to calculate u and v. So we have calculated u and v in this way. Okay. So after finding this, we write it. So the complete solution will be CF plus PI. So this would be our final answer. So there are some tasks for your practice. So with this discussion, so I think this variation of parameters method is actually over now. Okay. So in the next lecture, we will learn simultaneous differential equations. How to solve simultaneous differential equation.